All right, so here we are again with our introduction to limits, numerically and graphically, and understanding limits. We left off with finishing up this last example of seeing, okay, f of 2 exists here. It is the value of 4, but the limit as x goes to 2 of f of x does not exist here. The reason why, again, is I approach x, as I approach an x value of 2 from the left, so that is this piece, because this piece exists to the left of 2, I'm approaching a height or a y coordinate of 4. As I approach an x value of 2 from the right here, I'm approaching a height or a y value of 1. Even though that doesn't exist, I'm still approaching it, right? It doesn't have to be there for me to be able to approach it. So, if I look at those two y values, they don't match up. So I'm not approaching the same L. Therefore, the limit does not exist. So to kind of recap these three examples, we saw the first one. This is an example where the function exists at x equals 5, and it has a value of 3. The limit also exists at x equals 5, and it has a value of 3. So the function value and the limit value are the same at that x coordinate. Here, the function did not exist when x was 3 because there was a hole. But the limit did exist when x was 3 because it was still approaching the y coordinate of the hole. So the function doesn't have to exist at the point that we are checking the limit. As long as the function is still approaching the same value from both sides, the limit will exist. Here we see kind of the opposite. The function does exist when x is 2. It has a y coordinate of 4, or a height of 4. But the limit does not exist when x is 2 because we're approaching two different heights for the left and the right. Now I would point out on all of these examples, if I was looking at any other x value on that curve, the limit would exist, and it would be the same as the height of the function on the curve. So, for example, let's look here, right? So this is our y-intercept. Let's say this is the point 0, 5. I don't know, because it's a little bit higher than this, right? So the point on this function would be the point 0, 5. So f of 0 would be 5, and the limit as x went to 0 would be 5. Right? So I'm only trying to show you examples that are interesting situations where we have to think about it. If the function is just continuous at the point that we're looking, at the x coordinate that we're looking, then it's going to always be this sort of scenario where the function exists and a limit exists and they have the same value. So it's only at these interesting scenarios of holes or breaks in the graph or other interesting sort of graphical situations, asymptotes, which we didn't look at yet, where we have to think about, okay, what is it approaching the same value from both sides? All right, so those were some examples. Hopefully we have a better idea of limits. Let's look at my definition. So this is my definition of a limit in my own words, all right? Because again, this is the informal. If you want to look at the formal, just look it up. It's probably in your, or it is in your textbook, and you know, you could Google it as well. But if you think the informal is confusing, you know, the formal is not going to be any better. So here's kind of in my own words. So a limit is the height or y value a function approaches as x approaches a given value from both sides. That's what a limit is. So the key thing to understand here is that the answer to a limit, and I've kind of been talking about this, or not kind of, I have been talking about this as I was going through these examples, the answer to a limit, so in this case 3 or -2 or does not exist, is a height or a y value. That's it. You're given an x value, and you're trying to find a height or a y value. That's what a limit is. The only difference between evaluating the function and evaluating the limit as x goes to a point on the function is, for the limit, we're talking about approaching. For evaluating the function, we're talking about this is the value at this point. Our notation, and I have already been showing you this up here, but just to formalize it, we write it, the limit as x goes to c of the function equals L, right? So we would have to have some function. You could write the function in here instead of f of x. That doesn't matter, but you're going to have some c value that you're given for x, and you're going to have some output, which is the L that we referred to back up here in our informal definition. All right, so now let's talk about the methods of evaluating a limit. And the title of this video, remember, was Numerically and Graphically. So what does numerically mean? Well, numerically means use a table. What does graphically mean? Well, hopefully it's kind of self-explanatory. It means look at a graph, right? That's what graphically means. Analytically, so we're not going to focus as much on analytically right now, but if you continue to watch the videos for this unit, you will see more analytically, because that is usually how we are actually evaluating limits. But the most basic method is direct substitution, which means literally just plug in the point, or plug in the x value. And then there are also some other methods as well. And the other methods are going to involve more algebraic techniques, because in those situations, the direct substitution didn't work. Just to point out, on this problem here, so this is an example of direct substitution. If I plug in the value to the function and I get the same thing as the limit, then that's what I mean by direct substitution. Okay, let's do some examples. Okay, so here we are looking at numerical examples. So I have this function, f of x equals 3x minus 6 over x squared minus 4. And I've already plugged this stuff into the calculator and done the tables for us, and remember, the table is numerically. But I do want to show you how to change your calculator settings so that you can do what I have here with the x values, and this is how we would want to see the limits. Because remember, when we say as x is approaching a given value, we want to get really, really close to that. So the value we're looking at here is 1, but 0 is not close to 1. 0.9 really isn't that close to 1, right? I got to do like 0.9, 0.99, 0.999. That's what we mean by getting close to 1. So when we say close to 1, we're not talking about 0 and 2. Those are way away from 1. That's not going to help us here. We need to get really close to 1, so we need to be able to type in numbers. So if I go to my calculator, you can see I already have the function plugged in here, right? I could look at my graph. It's not terribly helpful. So the calculator is not great with helping with graphing, but it is good with helping numerically. So in order to do what I did, if I go to the table, right, this is just my normal table. So I want to do second window, which is table set, and I want to change the independent variable to ask. So typically we want it on auto because that allows us to just scroll, but ask allows us to enter in values. So now if I click on table, it's just empty, right? So this is where I can do the 0.9, and then 0.99, and then 0.999, and then we can do 1, and then 1.001, 1.01, and 1.1. So that is what I did to get these values. All right, so that's what we can see. I'm not going to go through that again, but that's what you're going to want to be able to do to evaluate limits numerically. Okay, so first let's talk about, well, what is f of 1? Well, f of 1 is 1, right? And we can see that right here. Okay, so what is the limit as x approaches 1? Well, I can see as x approaches 1 from the left, the y values look as if they're approaching 1. As x approaches 1 from the right, the y values look as if they are approaching 1. And in fact, I know f of 1 is 1. So therefore, I can conclude that the limit as x goes to 1 of f of x is 1. All right, pretty simple. How about this one here? So here, well, first let's evaluate what is f of 2. And if I go back up here, if I plug 2 into the function, I end up with 6 minus 6, which is 0, and then 4 minus 4, which is 0. So I get 0 over 0. What is that? Well, that's not a number, right? So f of 2 does not exist. We'll learn more later what we would actually call this, but for right now, we're just going to call it 0 over 0. Well, why is that? Well, let's factor a little bit, and this becomes 3 over x minus 2 over x minus 2 times x plus 2. Ah, now I can see. So when x is positive 2, I have a hole. But let's look at this numerical table, though. As x approaches 2 from the left, the y values look like they're getting really close to 0.75. As x approaches 2 from the right, the y values look like they're getting really close to 0.75. If I was to evaluate if I was to find the y coordinate of the whole, remember we find that by plugging the number, so 2, into the reduced function. So this would become 2 plus 2, which is 4. 3 over 4 is 3/4, or 0.75. I can see that the limit does exist, and it is 3/4. And again, I can see that from the table. So we want to be using the table right now. The one thing I would just point out with the table is it's hard to tell, well, do I know it's exactly 0.75, right? I don't know for sure by looking at the table. I could keep getting closer. So in my calculator, I could do 1.9999, 2.00001. But that is how I would look at it. How about the next one? So here, we want to evaluate when x is -2. What happens when I plug in -2 here? Well, I get 3 over 0. That's not good. So this also does not exist. But why is it in this case? Well, in this case, it is because we have a vertical asymptote. Now, let's look at the table though. So as x is approaching -2 from the left, these values are getting really becoming very large negatives. As x approaches -2 from the right, these values are becoming very large positives. So the graph is not going in the same direction. If I actually look at the graph here, right, here's -2, I can see this is going up, this is going down. Those are not approaching the same height. So therefore the limit also does not exist. Because in order for the limit to exist, we have to be approaching the same height from both the left and the right. These aren't even approaching a height, let alone the same height. All right, I want you to try some examples. So evaluate the limit as x goes to 0 of this function. Also notice here, this is the first time where we're seeing, instead of writing f of x right here, I'm actually just putting the function in. That's the same notation. So evaluate the limit numerically or graphically. I'd recommend numerically. Pause the video, unpause when you're ready to discuss. Okay, did you get 6? Great, me too. Excellent, let's move on. I'm just kidding, let's talk about it. Okay, so here, I went to my calculator, I put the function in. Be careful, make sure to put the entire denominator in parentheses. And then I went to my table. I know I'm approaching the limit as x goes to 0. So I did -0.1, -0.01, -0.001, and then 0. 0 didn't work. And then 0.001, 0.01, and 0.1. Okay, so the function doesn't exist at 0, but as I approach 0 from the left, and as I approach 0 from the right, the y coordinates look as if they're getting really close to 6. So I said the limit as x goes to 0 of x over the square root of x plus 9 minus 3 is 6. Boom, that's it. Okay, let's do 2 more. So I want you to evaluate these, again, on your own. I would recommend doing these graphically. So this one I would just actually kind of draw it by hand, and this one I would either draw it by hand or use my calculator. So pause the video, unpause when you're ready to discuss. Okay, so for the first one here, the limit as x goes to 5 of f of x, where f of x is this piecewise function, is 1, but f of 5 is -2. Wait, so the limit can exist and the function exists, but they don't have to be the same? Yeah, here's a good example of that. So remember this, if we understand the piecewise function, this is just a horizontal line at x equals 1, at y equals 1 everywhere when x is anything except for 5. So as I approach 1 from the left and as I approach 1 from the right, the height is 1, so that's the limit. But when x is when x is 5, the height is -2, because that is this point. Okay, next one, this doesn't exist for both of them. Why is that? Well, we've seen this function before. X over the absolute value of x. This is a horizontal line at x equals 1 and a horizontal line at x equals -1, but at 0, it does not exist. So as I approach 0 from the left, I'm approaching a height of -1 because that is my height. As I approach 0 from the right, I'm approaching a height of 1 because that's my height. Those don't match, so the limit doesn't exist, but also at 0, the function doesn't exist. So limits, what is the height or y value that we are approaching at a given x value as we approach from both the left and the right? Graphically, look at the graph from left and right. Numerically, look at the table from left and right. Boom, calculus. That's it.